Right, this video is going to take you through diffraction gratings. I suspect it might be a little bit long, so it's in three sections. Firstly, deriving the diffraction grating formula. Secondly, talking about lines per millimetre, what on earth that is. And thirdly, an explanation of why you get very sharp, bright dots from the diffraction pattern with nothing very much in between them. I'm assuming that you've seen the pattern produced by a diffraction grating. If not, I'll link to a video which shows the pattern, so you know what we're talking about here. So a diffraction grating is basically like a single slit or a double slit, except it's just lots and lots and lots and lots and lots of slits. So here's my diffraction. Oops, it's all grouped together. My diffraction grating is this dotted line. It's just a lot of slits, hundreds of slits, thousands of slits on a piece of glass or something like that, so that light can only get through the gaps and not through the bits where it's blocked. Got a laser being shone on it. That's just a handy source of coherent light, and also a screen. Now you notice that the screen here is curved. That's often the setup if you're, depending on what you're using the diffraction grating for, often you'll have a circular screen centered on the middle here. That's also just going to make our derivation potentially make a bit more sense. So, laser light shone on the diffraction grating. As you should have seen, we get a series of dark spots. What am I talking about? Bright spots on the screen. If you had a flat screen, it would look largely similar, except the spacing would start to increase, and nothing in between. Okay, so we get these bright dots, but with nothing in between them. Okay, darkness. Now, what's going on? Well, if we zoom right in on the grating, and this bit here is like a beam of laser light coming in, hitting quite a lot of the slits, all the light then goes off to the right and hits the screen. Now, the light hitting a point on a screen, because the screen is so far away, these lines are emerging like basically parallel to each other. They look like they're parallel because we've zoomed so far in. Really, we're considering light going to one point on the screen, but approximating them as parallel is really going to help. Now, when these rays that we're imagining hit the screen, hopefully you should be happy that the path difference between each of the different rays from each of the slits is 0. So there's 0 path difference between any of these different routes. So they're all going to arrive in phase. Constructive interference, we're going to get a bright spot in the center of the screen, and that's what you would expect. Now if we go off center at some angle, which I'll label the angle here theta, there's another angle at which we get another bright spot. That must mean that there's constructive interference occurring there. For there to be constructive interference, the path differences, which I'm labeling in here with arrows, it's going to be quite hard to see the first one, but hopefully you'll see these ones here. These are all the path differences between the top beam, the top ray, and then each of the separate rays. Now at the first maximum off center, this is going to occur when we've got one wavelength of path difference here, 2 wavelengths here, 3 wavelengths here, 4 whole wavelengths here, etc. So there's a whole wavelength of path difference between the top one and the one below. That means we're getting constructive interference. This is the first maximum. Now we can, this little segment here, we can enlarge this triangle a bit, okay, to make things clearer. We have D, we're calling the separation between each of the slits. We've got our path difference, which we just decided is lambda, 1 wavelength, and hopefully you can convince yourself via some nice maths that this theta here is the same as this theta here, because I've drawn this line so that it crosses the rays all at right angles. Okay, convince yourself of that. That means that this is therefore theta. So we've got a 90-degree angle there. That means this is the opposite and this is the hypotenuse, so we can say sine theta is opposite lambda over hypotenuse d, or alternatively d sine theta equals lambda. That's the condition for the first bright maximum off center. Okay. Now you've probably guessed where this is going already. If we continue to increase the angle that we're looking at, we're going to get to another point where we're going to get another bright maximum. Okay. Now the path difference between the top and the second one down is going to be 2 whole wavelengths. This is going to be 4 whole wavelengths. This is going to be 6 whole wavelengths, etc., etc. It's all going to be a whole number of wavelengths, and now they're all multiples of 2. Okay. Once again, we've got this angle theta, which is also this angle theta. So we can take this triangle here. Now this triangle is d theta 2 lambda sine theta is 2 lambda on d. D sine theta equals 2 lambda. Now we can generalize this because this is exactly the same as the other formula, except the other formula just had lambda. That was the first fringe off center. This formula has 2 lambda, the second fringe off center. So we can just generalize that and call that n. So now we have this formula where d sine theta equals n lambda, where n is the order, it's called the order of the fringe. Okay. Now the numbering system is important. The 0 order fringe, make that a big 0, the 0 order fringe is the central one. Okay. The first order, remember, this was the first fringe here off center. It was 1 wavelength difference each one. The second one was 2 lambda. So the first order, first order is the first one off center. The second order one is the second one off center. Now this works both ways. So if I skip all the way back here, okay, now center of the screen is here. This is the 0 order fringe. This is the first order fringe, the first fringe off center, and so is this. They're both the first one off center on either side. This is the second order fringe, that's the second order fringe, this one is third order, etc., etc. So that's the fringe numbering system. That's the number you put into n, your formula here. So you can use this formula to work out any of the components of this, given that you know the other bits. So the formula is d sine theta is n lambda. The only thing to mention, so this is the second of the bullet points at the start of the video, we don't always get told or get asked for d. D is the separation between each of the slits. You might be told it, and indeed if you look at a diffraction grating, if you get one, it might have D labelled on it, but more likely it's going to have the number of lines per millimetre, or the number of slits per millimetre, or the number of rulings per millimetre, or whatever written on it. This is how many slits there are per millimetre. You need to be able to translate between this and D. Okay, it's not rocket science, but you just got to be careful of units. Okay, so if there are 300 lines per millimetre, that means there are 300 slits in 1 millimetre. That means each of the slits is 1/300th of a millimetre apart. Okay, but ordinarily we want to put D into this formula in meters. Okay, so 1/300th of a millimetre we've then got to convert that into meters. Okay, so have a go at that, converting 300 lines per millimeter into fringe spacing in meters. Do that now. I'll just pause the video and then we'll check what you've come up with. Okay, so the separation between each of the slits is 1/300th of a millimeter, which is, if we round it, it's recurring, 3.3 times 10 to the minus 3 millimeters. That means that the slit spacing in meters is going to be 3.3 times 10 to the minus 6 in this case, because we've converted from millimeters to meters. So you've got to be able to convert one way and the other between lines per millimeter and meters of slit spacing.